Question 31. The diagram shows a typical circuit. Determine the effective resistance of the whole circuit. Now, we've got a couple of things here. We have these two in this branch B. We've got this 1 and 2 ohms. So we've actually got an effective resistance there of 3 ohm between these two. Because they're in series, we can just add them up. Same here. This is 1.5 ohm between these two. And therefore, if I work out the resistance for the parallel, I can do it down over here. 1 over R for the parallel will equal 1 over 3 plus 1 over 1.5. So 3, our common denominator is going to be 1 plus 2. And so 1 over RP is equal to 3 over 3. Our RP obviously is going to equal 1 ohm. So we have an effective resistance here for this branch is actually 1 ohm. And so our total resistance, determine the effective resistance for the whole circuit, is going to be this 1 ohm plus this 1 ohm over here. The total resistance is going to equal 2 ohm. Then it says determine the currents flowing through each of the network resistors. Now, to do that, I need to firstly work out what is my overall current. Now, our I total would be your total voltage, which is 1.5, divided by your total resistance, which is 1. So it's 1.5 amps. So we have in the circuit 1.5 amps flowing. Okay, so in looking at that then, if I just now take that away, got a good idea of what's going on there. I now want to work out the currents in each network resistor. So basically this 1.5 amps is going to flow. It's going to divide here like that, and then it's going to come back. So I know, for instance, that through this resistor over here, it's also going to be 1.5 amps, because all the current will come back together and will flow through as in a series circuit. But what about through B and D? Now it's going to split up according to the resistance. Remember, we said, as we showed earlier, you've got an effective resistance here of 3 ohm and 1.5 ohm. So you're going to have your current splitting up in that ratio, but it's in the inverse ratio. So it's 3 is to 1.5. We could also write that if I just divided this by 1.5 each, that's in the ratio of 2 is to 1. Now, the two parts will actually go through the resistance of 1.5, and the one part will go through the 3 ohm effective resistance. So we've got a total of 3 parts. I take my 1.5 amps, I divide that by 3 and I get 0.5. Now 0.5 will go through the 3 amps. So through this section over here, we're going to have 0.5 amps, and through this section over here, we're going to get 1 amp flowing through. I hope that makes reasonable sense. We then have, it says, determine the potential difference VAB and VAD. So perhaps if I just close all of this, hopefully we'll remember all the values that we have. Remember, we have a 1.5 amp here, and we've got going down here is 1 amp, and going through there is 0.5 amps. So it's going to be important. So going from A to B, VAB, that's equal to I times R. That's going to be going through there. So your potential energy drop per coulomb, your V across there, would equal your 0.5 times your 1, so it would be 0.5 volts for VAB. For VAD, you've got a similar sort of situation. You've got a 1 amp going through there. Your potential energy drop per coulomb, your energy drop per coulomb is going to equal your 1 times 0.5, so it will also equal 0.5 volts. And so there is an equal drop between the two, and therefore the potential difference between B and D, if I put a voltmeter like that, that would read 0 volts between the two.